Jamb 2026 candidates, you are welcome to today's lecture. We have to continue with the second half of our physics, Operation Destroying the Jamb UTME 2026 syllabus. All right. So get your notebook and your pen to jot down whatever you understand in this lecture. We are continuing with light energy, as recommended, as suggested by Jamb in their syllabus. All right. So light is an energy. Okay. It is not just an energy. It's not merely an energy. It is an electromagnetic radiation that enables vision. So light is an electromagnetic radiation that brings about vision. When you say it is electromagnetic, it means that it can create attraction. It can bring about attraction, or it can create a field. So light is that electromagnetic energy that brings about vision, or light is that electromagnetic, radiation that brings about vision. So light travels in a straight line at 3 × 10⁻⁸ meters per second in a vacuum. This is the speed of light. Expect to see something like this in your Jamb UTME, okay? Your Jamb UTME 2026, expect to see something like this, okay? The speed of light, 3 × 10⁸ meters per second in a vacuum, The speed of light in a vacuum. Remember, sound does not travel in a vacuum, but light travels in a vacuum. So, under the sources of light, we have natural sources, we have artificial sources. Now, let's look at the natural sources of light. They include anything natural, created by nature, not man-made. We were born into the earth to discover that this thing is a source of light, making it natural. It's not man-made, okay? All these artificials are man-made. So natural is, example, sun, stars, fireflies, okay? For example, under this natural, example includes sunlight for photosynthesis, okay? It's a radiation, okay? Electroviolet light, okay? A radiation for photosynthesis. Then under the artificial, you have bulbs and LEDs or LEDs, LED light, this common white light you see, white light of today that consume minimal energies, okay? You have lasers. For example, under the artificial sources of light, you have the street light you see, street light illumination you see in your streets, okay? Your light at home, all those artificial lights. All right. Now, let's look at luminous objects and non-luminous objects. When you hear the word luminous, lu means light, okay? Light. All right. So, luminous object is an object that emits their own light. They emit what? Their own light. That's why they are luminous. That's why they are called luminous objects. They are able to do what? To emit their own light. Luminous objects. All right. For example, they include sun and bulb, so they can emit light by themselves. So luminous objects can either be a natural source or an artificial source, okay? Then non-luminous object is an object that reflects light, okay? This object reflects light, all right? So when light is focused on them, they reflect light. For example, moon, okay? The moon reflects light. I don't know if you have come across this concept called solar eclipse and lunar eclipse, okay? The lunar eclipse where the moon reflects light to the earth, okay? Some part of the earth receive the light reflected by the moon, while some part of the earth is dark, okay? Due to umbra and penumbra, all right? So, book is also an example. That's paper, okay? So non-luminous objects are objects that can reflect light, that can, shoot back light. When light ray is incidented on them, or when you focus light ray on them, they do what? They bounce back light ray instead of absorbing it, okay? Example can be a white background, a white wall, a white paper. That's why you are seeing book here. Now, let's look at the propagation of light, okay? Under the propagation of light, propagation means multiplication, movement, all right? The first we have here is the speed of light, which is this small letter c. If you remember the Albert Einstein formula, where E is equal to, mc squared. All right. So this C stands for light, the speed of light. All right. 3 × 10⁸ meters per second in a vacuum. Okay. The speed of light is slower in medium or in media, such as water. And the speed of light in water is 2.25 × 10⁸. The second here is frequency, F, and wavelength. So this is related by C, which is speed of light, is equal to what? F times lambda, which is frequency times wavelength. All right. So this is the relation between frequency and wavelength. In case you want to use this formula to solve, all right, where you have speed of light, you have frequency, you have wavelength as your parameter, depending on what you are given. If you are given speed of light, you are given frequency, and you are told to look for wavelength. What do? You make wavelength, which is lambda, the subject of the formula, and solve. You get your answer. Shikina. All right. So higher frequency means shorter wavelength. All right. So higher frequency, when the frequency is high, there is short wavelength. Do you remember the Rogue wave, the dispersion of light? Do you remember the revox, the electromagnetic wave? The higher the frequency, the shorter the wavelength. The higher the wavelength, the shorter the frequency. As easy as that. So for example, red light has longer wavelength but lower frequency. Remember, Rogue wave, which is the rainbow. Arrow stands for red, and red is the first. So it has the longest wavelength and the lowest frequency. Shadows. Shadow is formed when light is blocked. So when you block light, shadow is formed. Now so shadow take the form. When light ray is blocked, that's when you see shadow. Shadow will now be casted. It's that opaqueness of that object, okay? It's going to cast the shadow because the object is opaque. it is going to do what? Cast a shadow, because light can pass through. Shadow is formed, and when a shadow forms, you can see two layers of that shadow. It's going to form two layers, okay? The first layer is umbra, and umbra is a portion of total darkness, okay? Then the second one is penumbra, and penumbra is an area of partial darkness. The next here is eclipse, and we have two types of eclipse, okay? We have solar eclipse and lunar eclipse. The two most common types of eclipse, solar eclipse, lunar eclipse, all right? So solar eclipse is a phenomenon whereby the moon blocks the sun. When the moon and the sun in the solar system, when they are in the same line, okay, the same angle, okay, the same plane, okay, the moon is between the sun and the earth, all right? So the radiation from the sun is not meeting the earth directly. So the moon will now block the earth or absorb some of the radiation. Because the moon is opaque, light doesn't pass through. It's going to make that portion of the earth that is blocking to be what? To be dark. All right, you are going to see umbra there. You are also going to see the other portion of shadow, which is penumbra. All right, so that's when you see darkness during what? Solar eclipse. The moon blocks the sun. That's what? Solar eclipse. So that's when you see during the day, you can see darkness. Okay, you see darkness on earth because of this shadow casted by the moon, all right, onto the earth. All right, so we have lunar eclipse, and lunar means moon, solar means sun. So lunar eclipse is when the earth's shadow on the moon, all right, the earth's shadows on the moon. That means the earth is between the sun and the moon, all right. So the sun radiates light energy on the earth, okay, because the earth is opaque, okay, or opaque. The earth does what? It strikes a shadow, or it casts a shadow on the moon, all right. So the shadow of the earth, you are going to see it visible on the moon. Easy way to remember is, in solar eclipse, the earth is between the moon and the sun, while in lunar eclipse, the moon is between the earth and the sun. Pinhole camera. The pinhole camera forms inverted image due to straight line propagation. Because the propagation of light ray in the pinhole camera is straight, the movement of light ray in the pinhole camera is straight, it produces an inverted image. When you say inverted, image turns upside down in the pinhole camera. Take note of this. The distance from the hole to the screen, that's the pinhole to the screen, that distance from pinhole to the screen is equal to or the same as the object distance for sharp image. Okay, so the distance from the hole to the screen is the same as the object distance for a sharp image. All right, so when you are calculating, you are carrying out calculation related to pinhole camera, please take note of this, because they might give you the distance from the hole to the screen, and the formula says you need object distance. So what you have to do is to use the distance from the hole to the screen as the object distance. This is the diagram of the lunar eclipse. Remember, lunar means moon, all right? So what did we define? We discussed that the earth is between the moon and the sun, all right? This is the sun, this is the earth, this is the moon, all right? So the earth casts what? Shadow on the moon, okay? You are now going to have a penumbra around here, and here will now be umbra, because you are having penumbra here, that's area of partial darkness, because some of the light ray diverges, okay? It's not all the light ray that will go straight, but this part that is directly blocked by the earth, so the shadow around here is going to be of the total darkness, which is the umbra, because the earth is opaque, okay? Light ray doesn't pass through, so it's going to cast a shadow. So the part that it covers fully is going to experience what? Umbra, which is total darkness. While the part like here that it doesn't cover fully is going to experience what? Penumbra, which is area of partial darkness. All right. So the moon is going to experience darkness. This is the diagram of the solar eclipse. In the solar eclipse, this is the sun. Remember what we discussed? We discussed that in the solar eclipse, the moon is between the sun and the earth. So this is the moon, and this is the sun, this is the earth. So the moon is smaller, and the earth is bigger than the moon. So the moon blocks light ray from hitting the earth directly. All right, so this, because the moon is opaque, it casts a shadow too on that portion of the earth. So that portion of the earth that the moon casts a shadow on is going to be dark. That's why you experience darkness in some region during what? Solar eclipse. All right, so some parts we experience partial darkness, and some parts we experience what? Complete darkness, which is the umbra. Penumbra is partial darkness, so umbra is complete darkness, the area that the moon directly blocks. All right, this area now. All right, now the pinhole camera. Let's understand how the pinhole camera operates. The pinhole camera works under the principle of the rectilinear propagation of light. When you say rectilinear propagation of light, it means the propagation of light on a straight line. All right, on a what? Straight line. All right, so light travels in a what? In a straight line. That is the propagation. Remember, an inverted image is formed, okay, in a pinhole camera, upside down image. All right, a small hole allows light ray from an object to pass and form an image on the screen. So because of that small hole that is there, light passes, and you know that when light passes through a small hole, what does it do according to the properties of wave, the characteristic of wave? What does it do when light passes through a small hole? It spreads. That's what is called diffraction. It spreads and is propagated in a straight line, and it casts an image, an inverted image, on the screen. This is the diagram of the pinhole camera, illustrating the pinhole camera. This is the box, all right? This is the pinhole, all right? The pinhole, all right? So this is the object. It was written as subject here because that is what we are trying to create an image of. Okay, this is the light ray. Okay, this is the light ray thrown by this object. So light ray fall on this object. Okay, this is a balloon. Light ray fall on this object, so the object absorb the light and form its own light. Okay, the light bounces onto the pinhole of the camera, and it casts an image here. All right, it casts an image on the screen. This is the screen of the pinhole camera. Okay, and you can see the balloon now. The balloon now is now upside down, different from what we had here. Okay, you can see it's now upside down. The rope is now up. The balloon down, but here the rope is down, balloon up. So inverted image, upside down in a pinhole camera. So upside down image. All right, as easy as that, easy peasy. Still under the pinhole camera, the formula we use in calculating image size in a pinhole camera is image in a pinhole camera. It's very easy. Image height over object height is equal to distance of image from pinhole over distance of object from pinhole. So you can use any of these formulas, okay, to solve for the image size of a pinhole camera. All right, you can either use image height over object height, that's if you are giving image height and object height in your parameters, okay, or you can use distance of image from pinhole over distance of object from pinhole. Very easy. You can use any of the two. If they give you distance of image from pinhole, you use this one, okay, depending on the one they give you. But they can still give you in a scattered way. They will give you distance of object from pinhole, they will give you image height, okay, and they can give you distance of image from pinhole. They will give you just three. All right, so what are you going to do? You are going to what? Substitute and solve like that. Okay, you divide this by this and you times this by this, as easy as that. All right, basic mathematics. Then how do we calculate the magnification of the pinhole camera? It's very easy. M, which is magnification, is equal to image height over object height. That's what we have here. That's simple, easy peasy formula of magnification. Now let's look at an example to illustrate that formula we just talked about. All right, object height is equal in the question. Now let's say the parameter they give us, object height is equal to 10 centimeters. Okay, distance, object distance is equal to 200 centimeters. Okay, always remember that the unit is always in centimeter. If you are given in millimeter, convert to centimeter. All right, so screen distance is equal to 20 centimeter. Easy peasy. So how do we solve? Image height is equal to what? Distance. So how are we going to solve? It's very, very easy. All you need to do is to substitute. We already have our what here? Our object height here, which is what? 10 centimeters. Okay, that's what you are having here. Times. Okay, object what? Height. All right, so this one is our distance. Okay, distance, image distance. Okay, that's what you have here, 200 centimeter. Okay, this one is screen distance. That's the distance from the pinhole to the screen. All right, that's 20 centimeter. So 20 over 200 times 10 is equal to 1 centimeter. This times this will give you what? 200 over 200 equal to 1 centimeter. So the image height is equal to 1 centimeter. Remember, we use this formula. This is the formula we use, this formula. So we made image height the subject of the formula. Okay, that's why you're having object distance times distance of image from pinhole over distance of object from pinhole. That's what you have here. So since you are looking for image height, can you see? Object distance over this distance, okay, from pinhole, okay, times what? The screen distance, okay, from the pinhole still. Look at it. Distance of object from pinhole, distance of image from pinhole. So this is the distance of object from pinhole. This one, screen distance, is the distance of image from pinhole, okay, image distance. As easy as that, easy peasy. I always tell you, make subject of formula for what you are. Look at the same thing that I explained to you, that they can give you one, they can give you three, and leave out one. Okay, you are going to make what you are looking for the subject of the formula and get your answer easily. Physics is so easy. Jamb is so overrated. Now let's look at the reflection of light at plane and curved surface. How does light behave when it is focused on a plane surface or a curved surface? How does it behave? What's its characteristic? What's its property? Okay, let's find out. Okay, reflection occurs when light bounces off a surface. When light bounces what? A surface. That's reflection. Light ray falls on my skin and it bounces off. That's how you are able to see my color. That's how you are able to see me. The light ray that falls on my skin bounces off and it enters your pupil down to your retina, and your retina interprets it, send it to your brain interprets it as so person, or so color of skin, so complexion, through reflection. So what is the law of reflection? The law of reflection states that angle of incidence is equal to angle of reflection. So the angle of incidence is the same as the angle of reflection. That angle that you use to incident the light. Incident means the angle that brings the light, the angle that the light carries to come. That angle where the light when it fall on the object is equal to the angle of reflection. That is equal to that angle where the light bounce off the subject or the object. So it comprises of what? Incident ray, like the ray when it come, okay, from the light source, coming from the source, okay. Then normal. This normal is an area of, is like neutral area, okay? Nothing is going on there. It's usually angle 90, normal, okay? Nothing is going on there, the point of no reflection, all right? So then the third one is reflected ray in the same plane, okay? So as the incident ray falls on the object or the subject, it does what? It bounces off, all right? At another angle, which is the same as the angle of the incident ray, okay? Okay, it bounces off at another angle, and that ray that bounces off, that ray is called what? The reflected ray. And what is the application of a reflection of light in a plane or curved surface? The applications include in mirrors for imaging. You have plane mirror, you have curved mirror, all right? Another application is in periscope. What is periscope used for? Periscope is used to view closets, tiny closets, where you say your eye no fit enter, place where bend. That's what you use. You use periscope to view it. And periscope is simply two mirrors at angle 45. You place two mirrors at angle 45 like this. This is angle 45. Two mirrors at angle 45 like this. This is a periscope. Okay? One mirror, second mirror, first mirror, second mirror at angle 45. So this is a periscope. It's used to view what? Over obstacle. Where if you say something they block, you can use a periscope to view it. It's mirror. Okay? This reflects on this. This reflects on this. And we see the image. It's also used in what? In kaleidoscope. It's used in kaleidoscope. And a kaleidoscope forms multiple reflection for patterns. Okay, so kaleidoscope gives pattern with what? Multiple reflection. It has different mirror in it that gives different reflection and gives us patterns. All right. So it's also used in what? Sextants. All right. What is sextant used for? To navigate through obstacle. It's used for navigation. All right. Navigation, movement, easy movement through closets. All right. Now let's look at the diagram of the law of reflection. This is a plane mirror. All right. A plane mirror, anywhere you see they use this thing like this thing, just put this thing will be like a rig for. Just know that's a plane mirror. All right. So from point what? From point A to point what? B. All right. So you can see 0 here. This is the point called the normal that I told you that is a point of no reaction. So this one is the incident what? The incident ray. The incident ray of light from the source. All right. It is from the source. So when this ray of light is incidented on the mirror, it falls on the mirror and it bounces off the light ray because the mirror is a non-luminous object that bounces off light ray. It bounces off the light ray. So immediately it bounces off the light ray, the reflected ray is formed. And it is formed at the same angle. As explained by the law of reflection. The angle of incidence is equal to the angle of reflection. Alright, so the same angle. The same angle 45, angle 45. So now you can see the angle. It gives us the formula of theta. This is what we have here. Theta I, which is theta incidence, angle of incidence, over theta R, which is angle of reflection. So the formula is angle of incidence over angle of reflection. As easy as that. This is also another diagram illustrating the same thing in a different position. So this one is the plane mirror. The incident ray falls, or the light from the source falls on the mirror. As it falls for the mirror, what happens? The mirror bounces off the light because it's a non-luminous object, and the light turns towards the reflected ray. Okay, this is the reflected ray. It goes up. Okay, bounces off at the same angle according to the law of reflection. This one cannot be angle 45. Then this one will not be angle 30. No. The incident ray or the incident angle cannot be angle 70, and the reflected angle becomes angle 5 or angle 10. No. All right. So that's that for that. It goes with the same angle. That's what gives us the formula theta, which is the angle of incidence, theta I over theta R, which is angle of reflection. As easy as that. We are talking about the reflection of light ray on a curved surface. What we just discussed now is the reflection of light ray on a plane surface. Now we are talking about the curved surface. So this one is a curved mirror. You can see curved what? Mirror. So this one is two mirror. One is the convex mirror and one is the concave mirror. So this one is the concave. This one is the convex. So we are banking on this side as convex. This one we are banking on this inside as concave. Remember, concave curve inside and convex curve outside. All right. So the reflection of light takes place at the what? The concave surface. That's that area of the highest curvature. The area of the highest curvature. That's where the reflection of light occurs. That's the reflection of light here will occur here. Okay. In this concave mirror, at this middle, the area of the highest curvature here. That's where it's going to what? Occur in a curved surface. While here in the what? The convex mirror, this place is the silver coating. Now, you don't say now silver coating that they do mirror. Mirror is just glass coated with silver. Okay. So this place, this point, the area of the greatest curvature, that's here of the what? Of the convex mirror, is the place that the reflection is going to occur. That's where the light is going to reflect from. All right. Here. All right. So looking at the diagram we have here, in concave mirror, a ray of light. Okay, let's take this as the concave, all right, and take this as the convex. So we are using this inner part as the concave. We are using this outer part as the convex, all right. So in concave mirror, a ray of light passing through the focus after reflection goes to the principal axis. A ray of light passing through what? Through a concave mirror afterwards, the reflection goes what? To the principal axis. While in a convex mirror, a ray of light directed towards the focus after reflection goes parallel to the principal axis. So for the concave, it goes what? To the principal axis. But for convex, it goes what? Parallel to the principal axis. Image formed by mirrors. And the first we have there is the image formed by a plane mirror. What should we expect? What should we expect from an image formed by a what? A plane mirror. What is to be expected by us? We should expect that the image is virtual, that is not real. The image is upright, is standing upright, not inverted. The image is same size, no change in size. The image is laterally inverted. Okay? Laterally inverted like this. If the image was focused like this, you are going to see it like this in the plane mirror. Then for a convex mirror, the image is always visual. Okay, Always version, upright and diminish. So always have it in mind that plane mirror and convex mirror, they always give what? Virtual and upright images. All right, virtual and upright images. But the difference is that for convex, okay, you know that convex mirror gives a smaller field of view. Okay, it gives us diminished image. Remember, it gives a smaller field of view. Okay, but for plane mirror, it gives us same size as the image. The slight difference is that the image formed by a convex mirror is diminished. You know that the convex mirror gives a smaller field of view. That's why it's diminished. But the image formed by a plane mirror is same size. All right, same size as the object. You know that plane mirror doesn't change. It doesn't change the object that much. All right, unlike the convex mirror. So, but it's also laterally inverted. So, if I bring this thing like this, you can see, in the plane mirror, for example, the image that is going to form in the plane mirror is going to be like this, laterally what? Inverted. The other side is going to appear. So, for the concave mirror, that's the one that is different, depending on where you place the object or the subject. Where is the object placed? Okay, was it placed beyond the center of curvature? Was it placed between the focal length and the center of curvature? So, you should know that. All right. So, what is the mirror formula? A very easy formula, easy peasy. 1 over V plus 1 over U is equal to 1 over F. So, what this means is that image distance plus object distance is equal to focal length. Image distance plus object distance is equal to what? Focal length, or focal length is equal to image distance plus object distance. Where V is equal to image distance, like I just taught you, U equal to object distance, and F is what? The focal length. Okay, sign convention, U, which is object distance, is negative for real object. So when the object is real, put minus negative U when solving. All right, I already taught the shortcut of using this to solve. Anytime you have 1 over something plus 1 over something equal to 1 over something, what you have to do is, don't need to be doing that LCM long journey. No time for that. All you have to do is to times and plus. All right, maybe you want to solve for this to 1 over V plus 1 over U. Just do V times U over V plus U. Anything you get from timesing V and U, you divide it by what you get from plusing V and U. As easy as that. Easy peasy. You get your answer so fast. You can get your answer within 8 seconds in your Jamb UTME examination hall. Now, the formula for magnification of a mirror. This one is small letter M, magnification for a mirror. What do we use? When it is linear, we use what? M, which is magnification, is equal to the height of the image over the height of the object. As easy as that. Or you can also use this other formula, minus V, which is image distance, over U, which is object distance. Okay, you can use any of these two when it is linear magnification. All right, like magnification from plane mirror. All right, so when the image is angular, the image is formed at an angle. Okay, the magnification is at an angle. It's not linear, it's not straight. You are going to use this one. You are going to introduce the angles. Okay, M, which is magnification, is equal to theta, which is the angle. Theta, the theta of the image over the theta of the object. That's the angle of image over the angle of object. As easy as that. Easy peasy, shikina. You get your mark and you leave there. Now let's look at the image in concave mirror by object position. What happens? Okay, we are describing it with object position now. Okay, so try all your best to learn the ones you can learn here, especially this infinity. Jamb, they repeat this infinity where this infinity I don't see it like 2-3 times for inside Jamb past question. This infinity. All right, so the object far away, that's beyond the center of curvature. Okay, or it can be center or it can be center of curvature. Beyond the center, object placed far away beyond the center, the image is real, inverted, diminished. That's what it forms, just like what we explained when we were treating this concave mirror. We also talked about this. It's real, inverted and diminished. All right, then when you place the object at the center, this one is placed beyond the center, but here when you place the object at the center, you get real, inverted, and the image is same size. When you place the object between the center and the focus, what do you get? You get a real, inverted and magnified image. All right, when you now place this object at the focus, all right, image is formed at infinity. So when object is placed at the focus, image is formed at infinity. So when you place objects between F, which is the focus, and the mirror, you get what? You get a virtual, you get an upright and a magnified image. So when you say a magnified image, you are trying to say the image is zoomed. Okay, the image appeared more visible. Okay, you get more information of the image. That's a magnified image. You can either get a magnified or you get a diminished image. This here is the ray diagram, so that you understand what is meant by focus, principal focus, focal length, center of curvature, and all of that. All right, this is the ray diagram. All right, so you see this place is the principal ray. That's the first ray that was incidented on this lens. What you have here in the middle is the lens. All right, this is the lens. So here the middle of the lens is called the optical center. Here is the what? The center of curvature. Here, the center of the curvature of the lens. All right, so here is the principal focus. The principal focus is the point at which you place the object and the lens can capture. It can be viewed from the lens. That distance that when you place the object, it can be viewed. Okay, it can be viewed and seen clearly. All right, that is the principal focus. All right, the principal axis is the central line that runs straight at the middle of the lens. Okay, it's like the skeleton of the real diagram. All right, this is it from one point to another, the principal axis. All right, so what is the focal length? The focal length is the length between the lens and the principal focus. That is the focal length between the lens and the principal focus. That's between the lens and the place where the object can be placed and captured by the lens or the mirror or whatever. So from the screen, okay, to the lens, from the screen or the retina to the lens is called the object distance. Then from the lens to the principal focus is called what? The image distance. That's from the lens to where you place the image is the image distance. Then from the retina or the screen, okay, depending on where the image is being casted upon, to the lens, that distance is called the object distance. That's from here to here. Now that you have understood mirror, the mirror formula, the angle of reflection, the law of reflection, and so on and so forth, let's now take some Jamb must repeat question to test ourselves to see how far we understood this lecture and how far we are ready to bulldoze Jamb UTME 2026. Jamb must repeat questions. Question 186. Which of the following is a natural source of light? A. Electric bulb. B. Sun. C. Torchlight. D. Candle. What's the answer? Drop the answer in the comment section. Share you sabi book. Question 187. The speed of light in a vacuum is approximately what? A. Blah blah blah. B. Blah blah blah. C. Blah blah blah. D. Blah blah blah. Share you know book. Drop the answer in the comment section. Question 188. Which of the following objects is luminous? A. Moon. B. Star. C. Book. D. Mirror. What's the answer? You know the answer, right? Drop it in the comment section. Question 189. Share you be scholar. In a pinhole camera, the image formed is what? A. Upright and magnified. B. Inverted and same size. C. Upright and diminished. D. Inverted and magnified. Scholar. What's the answer? Drop the answer in the comment section. Question 190. The frequency of light is related to its wavelength by what? A. Blah blah blah. B. Blah blah blah. C. Blah blah blah. D. Blah blah blah. What's the answer? You sabi book, right? You are a scholar, right? Drop the answer in the comment section. Question 191. The angle of incidence is equal to the angle of what? A. Refraction. B. Deviation. C. Reflection. D. Diffraction. What's the answer? Drop the answer in the comment section, my scholars. Question 192. In a plane mirror, the size is A. Real and inverted. B. Virtual and upright. C. Real and upright. D. Virtual and inverted. What's the answer? You are a scholar, right? Drop the answer in the comment section. Question 193. For a concave mirror, if the object is at the center of curvature, the image is what? A. Virtual and enlarged. B. Real and inverted. C. Virtual and diminished. D. Real and enlarged. What's the answer? You know book, right? Drop the answer in the comment section, my scholar. Question 194. Share you know book. You know all these things now. They be like my for where you did. The mirror formula is what? A. 1 over u blah 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 blah. B. 1 over u blah 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 blah. C. 1 over u blah 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 blah. D. 1 over u blah blah blah. What's the answer? Drop the answer in the comment section, my scholars. Question 195. A periscope works on the principle of what? A. Refraction. B. Dispersion. C. Reflection. D. Diffraction. What's the answer? Drop the answer in the comment section.